Hello everyone. We would like to thank you for collecting some flight radiation data for us. Gathering this information helps us gain a deeper understanding into solar flares and the impact of the radiation that they produce. By this stage, you should have bought a detector, collected your own data, and downloaded this raw data. Alternatively, you can also download and use one of our example data sets. If you started by visualizing your data, you should have produced a similar graph to the one in the top right corner. In this video, we will explain the Python code that we use to conduct a basic analysis on the collected data and show you how you can apply it to your own measurements. If you want to further your understanding, you can move on to a second stage of analysis after completing this. The basic analysis code follows the structure shown in this flow diagram. In step 1, we will make sure that you have downloaded the necessary raw data and flight-aware file. The code then reads through these files and extracts the data that we need in step 2. In step 3 and 4, the code goes on to create a new file with the necessary information. This new file will have a combination of the raw data as well as the flight-aware coordinates, if necessary. Lastly, in step 5, the code plots a variety of graphs that we use to visually analyze this data. To download the raw data from your detector, you will need to remove the micro SD card from the device and insert it into an external laptop or PC. The computer will read this SD card and allow you to copy the raw data file into the same folder in which you saved the basic analysis code. You can then refer to the FlightAware website using the link that we provided and type in your flight number. Download the corresponding FlightAware KML file into the same folder as the basic analysis code and raw data. To process this code, you will need to install and import the modules listed here. To do this, you can refer to Python's documentation linked here as well as on our website. Next, we define file_log and file_kml which store the paths to the raw data and FlightAware files. You will need to change these variables to match the name of your own raw data and corresponding FlightAware file. The next line opens the FlightAware file and parse through it using the pykml library. Sometimes, the detectors lose signal and are unable to record GPS coordinates. When this happens, we can still analyze the code by using the FlightAware coordinates to fill in the gaps between the raw data. The control variable is used to manage this. If your GPS data is available and accurate, each line in your raw data will have a GPS value A. If this is the case, you can set control equals yes. If the GPS has stopped collecting coordinates, the data entry will not have an A, and you can set control equals no. Next we will define a function to read the raw data file, extract the relevant information and sort it into categories including detector ID, date time, radiation count rates, latitude, longitude, and altitude. The variables data and data_GPS are created to store this information. The only difference between the two variables is that data_GPS only contains entries with a value A, indicating an accurate GPS coordinate measurement. We do the same thing for the FlightAware file. The read_kml function extracts the timestamps and corresponding coordinates and stores the data in the variables kml_time and kml_place respectively. The interpolation function is useful when the detector's GPS has lost signal and stopped recording accurate coordinates. This is where the data entry does not contain a GPS value of A. This function matches the FlightAware timestamps to those recorded in the raw file. If there are gaps in the raw data, the function uses the FlightAware coordinates to estimate the missing GPS coordinates and fill in these gaps. Our last step in reformatting the raw data is to put it all together in one new file. We do this with the write_nlog function. This function first checks if the raw data timestamp falls within the range of consecutive FlightAware timestamps. If so, it uses the raw data coordinates. If not, it makes use of the FlightAware coordinates. The function then determines the direction of the latitude and longitude coordinates. It combines each coordinate with its corresponding direction and adds the formatted data to the new file as a comma-separated string. Each data entry now reads, detector ID, timestamp, counts per minute, counts per 5 seconds, total counts, radiation data quality, latitude, latitude direction, longitude, longitude direction, GPS coordinate quality and some extra GPS information. Now we'll introduce a few functions to plot some of this data. While we have only plotted a few parameters, there are a variety of other plots that you can create using the new log file data. The plot_latitude function relates the latitude measurements to the radiation rate measured in counts per minute. When control is set to yes, it makes use of the raw data latitude. Alternatively, when control equals no, it will use the flight-aware latitude. The y-axis of this plot has been limited so that any radiation that was detected during the airport security check does not skew the graph. This limit can be changed as needed. Lastly, the x-axis is formatted so that the takeoff latitude is always plotted on the left, while the landing latitude is always on the right. Similarly, the plot_longitude function compares the longitude data to the radiation rate, again measured in counts per minute. It uses the same method and y-axis limit as the plot_latitude function. Next, we have the plot_altitude function. It also uses the same method to relate altitude in kilometers to radiation rate in counts per minute. An x-axis limit is set for altitudes of greater than 1 kilometer. Again, this is done to avoid any radiation measured at airport security checks prior to takeoff. 1 kilometer was chosen as majority of airports worldwide are at altitudes lower than this. However, this limit can be adjusted based off of the altitude of the specific departure airport. Our last graph depicts a color-coded flight path superimposed on a world map. The flight path is color-mapped according to the radiation rate experienced by the aircraft at each point along its journey. Any radiation values that exceed 95% of the maximum radiation rate are capped at the maximum level. This ensures that outliers do not skew the color map. A legend is plotted on the right with numerical values to give the color map context. Now that we have created functions to carry out all of our steps, we just need to execute these functions. The raw data is extracted from the file and the interpolation function is called. Based on the control setting, these flight-aware coordinates are then combined with the raw data into a new log file. This file will be saved with the extension new.log to the same folder as your raw data file. Using this new file, you can plot any other parameters that you may want to compare. The maximum dose is then calculated. Sometimes there is some radiation measured before the flight that can skew the maximum calculation. If your world map plot output is only one color or does not seem right, you can adjust the calculation to exclude the first 10,000 or so entries. Lastly, the code produces all the plots that were described in the previous functions. Thanks for watching. In the next video we'll explain what each of the graphs mean and what you would expect to see from your data.